the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode 31 of the Math and Physics Podcast, where today, as mentioned in the previous episode, is our 10K Q&A. Woo-hoo.
Let's go. Not followers, though. Just to
not
be clear.
Not followers
10K
yet.
downloads in total.
Downloads.
We got, well, right now we're at 12K. So, by the time we got to recording the 10K episode, we're at 12K. So soon we're going to be doing the 25K special.
I think it was more just like a, do you guys want to ask us questions kind of thing? It wasn't really like to celebrate. I mean, even though the 10K was pretty cool, it's mainly just a name gimmick, just to get a cool name,
We just wanted an excuse to do another Q&A, so now we're doing it. Also, we always have news in the beginning of every episode.
Every time.
So in other news, we are at 900 followers today.
Oh.
So if you are listening to this episode right now, on your phone, on your computer, if it happens to be on Spotify, please hit the follow button. We are almost at 1,000 followers.
That's
gonna be insane.
That's gonna be big. I think that's gonna be bigger than 10K. I think I've told you this before. Yeah. In my opinion, 1,000 followers means more than 10,000 downloads. Because followers is like, people who follow you. Like downloads is just that, okay, they could have just gone to our page and just downloaded an episode.
Yeah,
followers
but at the same
like
time, downloads
want to listen to you.
Yeah, downloads are worth more than like YouTube views, though.
Oh,
because,
are they?
Because on YouTube you can literally click on a video and click off of the video.
Oh, I guess
and
that's
it counts
true.
As a
Download
view.
it gets into. Yeah, I guess that's true.
Yeah,
I guess that is true.
Yeah. Anyways, so today we will be answering your question. Quick disclaimer before we actually start answering. We have like 15 questions, I think. So they're not going to be like super in-depth explanations. Also, some of the questions we're not actually like super qualified to talk about.
For sure.
So we're going to give like our understanding of the topic. Mm-hmm. And it might be wrong, to be honest.
Yeah.
There's a chance that it might be wrong. If we know that we're right.
Just our ideas.
Yeah. If we know that we're right, we'll definitely tell you. Be like, this is definitely it. But some of these questions...
Actually, say it the other way around. Like, if we know or if we think that we might be wrong, we will very clearly state it. We'll be like, hey, we might be wrong in this, but... And, say it. And there might be some things here on and off that we might be, a little factually incorrect about as well. So just assume that some things are wrong. But there are a lot of things where, especially in this episode, it's mainly the Q&A episode that this discussion is for, where there are a lot of things that we're going to just be like, that is definitely how this works. And we're just going to be explaining it.
Yeah. So, a lot of these are opinion questions. So those are going to be easy.
Yep.
Okay. First question. I'll introduce it. First question. What is your favorite podcast episode?
Oh.
Do you want to go first?
Sure. So my favorite podcast episode, I think a lot of my friends know this because I've been mentioning this a lot, but my favorite podcast episode is episode 23, Parallel Universes, because I don't know why. It's just a very interesting topic to me, even to this day. And it might be weird, but I love to listen to that podcast as well. Just listen to myself and Parker talk about parallel universes. Because I just think, the entire concept is really interesting. And there's so much more we can talk about it. That's why I just really love that episode. My personal favorite. What about you, Parker?
Awesome.
What's your favorite?
Well, I actually, as I was saying the question, I thought of an episode that I also liked. But, my original answer was episode 7, Condensed Matter Physics, with our physics professor, Stephen Julian. I found that interview to be super, super informative and interesting and intriguing. So it was awesome being a part of that episode.
Yeah, for sure.
Also, every time we have a professor on the show, it's always like we just ask a question and then we just sit and listen to like the wisdom
That's so true.
pour out of these like intelligent people.
Yeah,
And
that's very
just
true.
listening, sometimes it's out of the scope of what we know, but we can still appreciate like what they're doing and what they're explaining. It's crazy. So yeah, episode 7. But as I was asking the question, I actually thought of another episode, which is episode 2.
Oh,
That's right. Higher Dimensions.
oh yeah, that
was an
insane.
awesome episode. That was our
insane.
literally the second episode we've ever recorded, and it was so cool.
was
I remember
so insane.
explaining how it would appear to us if a 4-dimensional ball were to pass through our 3-dimensional manifold, I guess.
Yeah.
And
That's
that was crazy.
insane. Oh, I
was
forgot
crazy.
about that one. Our
Yeah.
original ones were actually like
Yeah.
the first 5, 6 ones were like basically just ideas where we thought it would be really cool to talk about, and I think they were really cool for sure.
Yeah, but there's also like honorable mentions like alien math,
Oh yeah.
life in the universe,
Oh yeah. For
quantum
sure.
physics,
For sure.
and also episodes with Matthew Cater. Those are always amazing.
For sure.
We have 3, 4 now, I think.
No, well, technically, if you count the part 2, we have 4. I think. Yeah, we have 4. Right?
Yeah.
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 Yeah, we do.
Yeah.
Okay.
Yeah.
Yeah, those episodes are always a lot of fun. And we're definitely going to have him on again.
Oh yeah,
so-
for sure. It's just really fun to talk to him because like he's kind of more. I mean, he is exactly our peer, right? It's just a year older. He knows more about our field, and we're in the same field as him, so it's awesome to talk about. So I think we're definitely gonna have him on.
He's kind of like a projection of what we're going to be in the future.
Exactly.
And I think of Matt as like a super, super smart guy because, this
for
guy
sure.
got a
For
4.0
sure.
in the
100%
year
I
that
agree
we're
with you.
doing right now. So, but I'm aspiring to achieve the same thing. So,
Yeah.
all right.
That's
Second
that's the
question?
goal. Okay, next question. The next question is a very, very interesting one. Can you speak on the potential connections between quantum physics and human consciousness?
So off of the bat, this is kind of pseudoscience. There's nothing that we really know
Well, there is a theory.
about
There's
what?
a theory called the quantum brain that actually I was reading just prior to this episode because I knew that I would have to know at least something to talk about this. So there's a theory called the quantum brain, and like the quantum brain theory, where basically classical mechanics can't exactly explain how processes in the brain take place. And the only way to explain such processes would be via quantum entanglement and, just quantum effects, basically. So the idea was that classical computers can never be as strong as quantum computers. And I think just a few scientists were like, hey, our brains are pretty strong. So what if our brains are basically quantum computers? Because what if every process can have multiple states, right? That's basically the idea of the quantum brain. I mean, that's the idea of the quantum computer. But that's also the idea behind the quantum brain. But again, I don't really know if we can prove it.
Well, I think one detail that you're missing is like why quantum computers are so powerful is because if you think of a classical computer, you have n bits, and each bit can either contain a 1 or a 0. So you can have 2 times n bits of information, right? But because of the way you can encode information into quantum, or they're called qubits, quantum bits, I think. Basically, you can have like a superposition of states, right? And so instead of having 2 times n amount of instead of having 2 times n, you have 2 to the n, which is exponentially, quite literally, bigger than what we have in classical computers. So basically you can perform calculations and whatnot exponentially quicker than regular computers, which is already pretty good.
Yeah, but it also takes it also takes a lot more power.
Yeah,
to run.
It would just be really
cold.
Yeah, it would be a lot better
as of right
on a
now.
quantum computer.
Yeah, as of right now. But yeah, that's a very interesting question for sure.
Well, we didn't really talk about consciousness though.
Yeah.
I wanted to say before you cut me off that
Sorry.
no, it's
Continue.
okay. That consciousness is not explainable as of now. You know, there's no real hard evidence that consciousness is a part of the physical world, I guess you can say. Mm-hmm. There's nothing that's really tying the fact that I know that I'm alive and I can move my hands up and down at will. And
there are so many philosophical things that you are talking about here. It's crazy.
Yeah. But there's just nothing connecting the fact that I know that I'm alive to my body and the particles that make my body. You know, there's nothing that we've found yet. So
well, there are philosophical theories on all these things, but
yeah, of course.
There's no actual connection. I think that's why it's been made a philosophy, because there just isn't an actual connection. I mean, I don't know. Yeah. Again, this is the question where we are definitely not sure. Not
this
qualified
can actually
to speak on this whatsoever, but we think. I mean, I don't think that there is a connection.
This can actually be an episode where we talk about it's going to be less of a physics episode and more of a philosophy episode where we try to, just have a conversation about the physical world and consciousness and what is not physical about reality.
I've always said I would love to do a philosophical episode because I think philosophy and philosophy of science is just a very important thing in science, and it's super cool. So actually,
I also think it's a requirement.
Yeah, if you guys want us to record a philosophy of science or a philosophy episode, put it in the comments actually, or send us an email.
That would be great.
DM us or tell us somehow.
We're definitely gonna do it anyways. But
yeah, I mean, I'm really convinced that we should definitely do it. Mm-hmm. Yeah, for sure.
So, third question. I don't know if this is the best way to answer this question is via podcast, but the question is, how do telescopes work? And I don't know. I think a better way would be to get some audio visual kind of explanations. But I can say okay, you have reflector telescopes and refractor telescopes. And basically you have curved lenses, curved mirrors that you point towards a section of the sky, let's say. Not even the sky, you can point it towards a tree that's far away. And the light that is coming off of or coming towards you from the direction you're pointing in will enter your telescope. And, depending on how your telescope is made, there might be lenses before the mirror or just goes to a mirror directly. But usually what happens is that there's a big opening, and then where you put your eye is a small opening. So what they do is they take a concave mirror, and that focuses the light into a smaller region, right? If you can imagine a bowl, if you shine the light into a bowl, all the rays will focus into a point.
Yep.
And so, once all of those rays are focused in, they get passed through some lenses, more mirrors, so that it can be shot out of the side of the telescope usually, or maybe the back if it's a refractor. And et cetera, et cetera. There are different types of telescopes.
Yeah, there are very many. The refractor versus reflector is also just how it's mainly.
Yeah.
In the reflector, there's a mirror, there's a parabolic mirror that then reflects it into another mirror that then reflects it into an eyepiece. Or again, depending on how the telescope is made, it can just directly reflect it into the eyepiece. Again, depends on how the telescope is made. But for refractors, sometimes the eyepiece could just be, in line with the mirror or in line with the lens. Sorry. So it just all depends, right? And yes,
And the reason why telescopes,
like a visual description would definitely be better. Yeah, sorry.
yeah,
Continue.
but the reason why telescopes are so like clear, I guess you can say, like there's no technology inside of a telescope. It's just, mirrors and lenses, but you can point it at the moon and see the moon very, very clearly. It's kind of mind baffling, but the reason is because there's no loss of information, right? All the information about the moon, like the visual information about the moon, is coming into your eye. But just because it's very far away and your eye isn't that great, you can't really discern the details. But when you put that information into a telescope that makes it easier for our eye to see, there's no loss of information. So that's why you get to see the magnificent details without having to, take a picture and zoom in. You just have it in front of your face. So yeah.
Also, interesting thing about telescopes is refractor versus reflector, and the fact that reflectors have, mirrors, is all the famous telescopes that you can think of, like the Hubble Space Telescope, or all the famous telescopes in space, all are reflecting telescopes, for the main reason that mirrors are just lighter to carry than lenses, and they're just a lot easier to construct than lenses. Because there's no lensing, there's no refracting happening in a reflecting telescope, of course. All they have to do is really transport this, this piece of metal with a few mirrors in it. Like it's not that heavy. But with lenses,
essentially that's what a telescope is, right?
Sorry?
It's just a telescope is just like a hunk of metal with mirrors in it.
Yeah, exactly.
So.
I mean, at least that's a reflecting telescope. Yeah.
Yeah. So we should get on to the next question.
Also, a reflecting telescope is generally a lot bigger, like a lot wider, and you can very well tell. Sorry, just had to put it in there.
Okay, so
big mirrors. Okay. So
question
next question.
4.
Okay.
Oh God. Okay, we are not moving quickly.
The next question is very interesting. What would happen if a black hole went into another black hole? That's a very interesting question. So, well, technically, a black hole would not really go into another black hole, because the way just gravity works is if there were just two rogue black holes chilling and one somehow comes into the gravitational influence of the other, what would happen is it would kind of behave like a binary system, or a binary black hole system, where they're just revolving or rotating around each other. They're technically rotating around a common center of mass, and whatever that center of mass is, they'll just keep rotating until they become closer and closer together. Now, depending on the size of both of these black holes, either one of them will just kick the other one out, or it could just, while they keep coming closer and closer together, they just become one even bigger black hole. So the the famous 2015 gravitational waves that were measured were actually from a black hole event, a binary black hole system collapsing into each other, becoming a bigger black hole. That event let out so many gravitational waves with such great energy that we could actually measure it, right?
Yeah, and just for reference, when we say like a binary system, it could be really anything. Like the Earth Moon is a binary system. It just seems as though the Earth is rotating around, or sorry, I meant to say Earth Sun.
Earth Sun, yeah. I was thinking about. I'm like, wait.
It seems, well, Earth Moon is a binary system, but anyways,
Earth Sun isn't really binary though, because there are a lot more.
Let me finish though.
Okay, continue.
So the Earth is rotating around the Sun, but actually it's not. It's both of them are rotating around a common center of mass, because the Sun is like 1,000,000 times bigger than the Sun. That center of mass is really close.
You just said the Sun is 1,000,000 times bigger than the Sun.
1,000,000 times bigger than the Earth.
Okay.
You know what I mean.
Sorry.
The center of mass is really close to the actual center of the Sun, so that's why it appears that way. But let's say we had two suns. The center of mass would just be in the middle. So both suns would be rotating in an ellipse. That's just a small detail, but we can assume circular orbits. They'd be rotating just around the middle. And so same thing happens with two black holes. They're just rotating around a common center of mass. And then eventually, depending on the characteristics of these black holes, some event will happen. Maybe one goes into the other. who knows?
Maybe one get kicked out.
Yeah,
Who knows?
that's right.
Who knows?
All right, so next question.
Yeah.
Why do you age differently in space?
Oh.
So we actually covered this in our special relativity episode, but just to explain it nice and short, concise, because the speed of light has to be the same in all reference frames, if you go very close to the speed of light, if your velocity is close to the speed of light, what happens is that consequently your time has to slow down so that the light can stay, well, not necessarily so that the light will stay at the same speed, but because the light stays at the same speed, your time is dependent on your velocity. Mm-hmm. So the faster you go, the slower your time has to be so that the light can not catch up but stay in the same.
It's
anyways.
Also no, but space is also mainly due to the gravity being a lot not a lot less, but because you're also so much farther away from the center of the earth, there's also gravitational time dilation that is also taken into effect, like a little bit, but you can still talk about it. And I think we also did cover this in our special relativity episode. I probably mentioned something about general relativity and gravity also depending, or time also depending on your gravitational influence. So because they're in a much less dominant gravitational field, or not technically less dominant, just farther away, that's why they can also experience gravitational time dilation, where your time slows down on a heavy mass. Yeah.
This question was asked in a way like why do you age differently in space? You don't actually age differently in space. You age the same. It's just depending on the speed you're going at, right? Like, you're not moving in your reference frame, but the Earth is rotating around itself and rotating around the sun. So it's versus your reference frame, the Earth has some velocity. And as I explained before, if you have some relative velocity versus another object, then the time that you're experiencing will be slowed down compared to another, or the other will be slowed down compared to you.
Yeah, I think compared is like the most important term in that sense, because like it's all about comparing. When you age differently relative to yourself, obviously you don't age differently at all. But the moment you come back on Earth, you're like, hey, he's like 5 seconds younger than everyone else. What? So there's that difference. It's all about comparing the ages.
That's right. So next question, why is the universe expanding? So that is a question that only God can answer. I don't know why the universe is expanding, but I can tell you, physically using like equations and things like that, I can tell you why it makes sense that the universe is expanding. I can't go to the edge of the universe and be like, hey, look, it's moving away from me.
No, but technically, we have seen proof, more or less, of the universe expanding, because when we see, 50 years ago, 100 years ago, when we point our telescopes at the sky, or technically not from Earth, but when we look at the so-called edge of the universe that we technically can't, but hypothetically speaking, the light coming from there can still be visual. But what we see in like 50 and 100 years is that we can see far much more light coming to us from things that we've never seen before. So galaxies and things that we've never seen before that seemingly existed, obviously, didn't exist in our observable universe. So what does that mean? The only explanation for that is that our observable, quote-unquote, universe is expanding. So is the universe expanding? Well, we don't really know. Is our observable universe expanding? Yes, because we can see that. We can see that the light from other galaxies is reaching us, and the galaxies are basically drifting apart from each other on average. It's kind of like that balloon example where you inflate a balloon. That's kind of what's happening to our galaxy. To our universe. Right.
One thing that's important to note is that the reason we know, or not necessarily the reason, but one way to imagine why our observable universe is expanding is because the light moves at the speed of light, right? and so if you are at a distance that is so far away from the Earth, and let's say it's a star that's emitting photons, and since the beginning of the universe, that light has been on a trajectory towards the Earth. Mm-hmm. Or not necessarily since the beginning of the universe, but since that star was formed, the very first photons that were emitted were on a trajectory towards the Earth. And it just so happens that, distance equals speed times time. The speed is the speed of light, but because the distance is so great that it takes, let's say, 5 billion years to get to the Earth. So as more time goes on, the more far away photons are reaching our eyes. And so the further into the universe we can see as time elapses. So that's why our vision of the universe grows with time, but we don't actually know where the end is. And that is actually a very good segue into another question that we have, which is, what is the size of the universe currently? Oh. And as we just said, there is no way for us to know that. There is zero way. And that is because of the speed of light.
Well, we don't know the size of the universe. We know the size of our observable universe, though.
Yeah, that's right.
Yeah.
So
it's like some 90 billion light years or something like that.
Yeah, there's only one thing that we can know, and that is just how far we can see. Beyond that limit of how far we can see, it could be complete blackness. It could be, a hyperbolic black hole that is surrounding our observable universe.
It could be literally anything.
Like beyond that boundary, it's just like we are in the black hole.
Like we have no idea.
Yeah, a fun thing about that is that we will actually never know.
Yeah, that's true. That's also true.
Because unless we go at the speed of light, there's no way we're going to be able to catch up to that boundary that is moving at the speed of light. Mm-hmm. So we need to go faster than the speed of light to catch up to the boundary and cross it. So according to the laws of physics, not possible. So turns out we're never actually going to know what's beyond our observable universe.
Yeah, it's pretty sad, but that's a sad reality. Okay, segue on to the next question. Oh, not really. At what age did you know you wanted to go into astrophysics? Okay, so I'm going to start this off.
Oh, no, yeah, go ahead.
Oh, sorry, did you want to?
No.
Okay, because I kind of wanted to say, when did Interstellar release? Whenever Interstellar released, wasn't it 2014?
Yeah, I was going to say 2014.
I think it was 2014. So 6 years.
Oh,
wow, that was 6 years ago. Oh, my God. That's crazy. So anyways, 6 years ago, I watched the movie Interstellar. And I think I've told this story before. I swear I have. But, yeah. So I watched the movie Interstellar. And basically, I had a lot of questions that were not answered by the movie. So what I decided to do was to search all these questions on Google, and that basically piqued my interest in astrophysics. So I'm not sure what age, but I'm 19 right now, so 13. I was probably 13, 14 years old when I wanted to go into astrophysics. Yes.
Mm-hmm. And for me, I was actually 17 years old. I already explained this story in one episode. I was in high school. I dropped all my sciences. I was going into business. And then I was on the website for U of T and I saw astrophysics as a program. And I was like, damn, I really have to do that. So I added physics to my schedule in high school in grade 12. I took it. I added calculus to I was already doing calculus because of business. But yeah, and then now I'm here doing astrophysics.
That's awesome. That's actually really cool. That's really cool. Yeah, I think we've both mentioned these answers before, but it's a 10K Q&A, so that's what we do.
Next question. Favorite class you've taken at U of T so far? Probably. Well, okay. Let's say classes we've completed. Okay.
Oh no!
So
what?
Yeah. Only classes we've completed because we don't know what's gonna come.
That's true.
In the classes that we're taking now.
That's true.
So favorite class that I've completed, I have to say, it's linear algebra.
Oh no, God damn. God damn.
You can have the same answer, but I honorable mention calculus 1 with proofs. The only reason I didn't like it as much as I should is because I was totally unprepared for proofs, and so I was kind of cursing my life at the time. If I was just a little bit more prepared for proofs, I think that would have been my favorite.
That's cool. That is cool. My favorite is also linear algebra. It's the courses I've done. Also because I think that course is really cool. I think it's really, really interesting. Because I don't think we've ever really done the level of matrices and the level of matrix analysis that we did in 223 in high school. I don't think we've ever done that. So I was really interested and satisfied after 223 because I was like, that was a really cool course. Plus, that is so applicable in like almost every single physics course we're taking.
Yeah.
Like 223 or linear algebra in general is a very important course, and I really enjoyed it.
And also, they start from 0 too. They literally start from what is like a coordinate.
Yeah, they started from bare basic.
Yeah.
To the point where I'm like, this is going to be so easy.
Yeah, and then they're like, what is a vector? What does it mean to be linearly dependent? What does it mean to be linearly independent? Mm-hmm. And then all the way from there to projections, matrices, linear transformations, eigenvalues, all that stuff.
Yeah,
that was
all
very
that
cool.
Good stuff. All that good stuff.
Next question.
Okay, next question. Would you go to space? Wow, that's a good question.
Well,
yes,
I think the answer
for
me... Yeah, the answer is pretty obvious. Of course I would go.
Yeah, if I had an opportunity to go, I mean, I know I would have to spend a lot of money. The money I probably wouldn't have. So if I just got an opportunity somehow, like, hey, do you want to go to space? For sure. There's no way I'm turning that down. I would
go to the moon any day of the year.
Yeah.
If somebody said, hey, do you want to go to the moon? I would be like, I would not even ask any questions.
I wouldn't even hesitate. Just
I would hop in the rocket and go to the moon, man.
Just hop in the rocket and leave.
Listen, I'm pretty sure only 9 humans have been to the moon.
Oh,
or
wow.
12, something like that.
It's a pretty low number, yeah.
But take in 108 billion humans have been born on this Earth, and only, let's say less than 20 have been to the moon. So it's definitely a percentage game here.
Yes.
Like going to the moon is definitely like the top of the bucket list.
But I think he's asking morally, would you go to space? Like, would I visit the ISS? Yes, for sure.
Yeah.
Yeah, for sure. Okay, next question.
Favorite celestial body?
Oh.
I don't know. I don't really know if I have a favorite.
Saturn with its rings is just crazy cool. Like,
that is cool.
I just think the entire planet is just really awesome. Like the rings look beautiful, first of all. Like they're just gorgeous.
That is right.
Just like it's just crazy. Crazy planet.
That is true. For me, I'm just gonna pick one. I'm gonna say it's Io. It's one of Jupiter's moons.
Okay.
The reason why I think it's cool is because there's frozen like hydrogen lakes or something like that.
Wait, isn't that on Titan?
Oh yeah, that is on
That's
Titan.
On Titan. That's Saturn.
Okay, I meant Titan. I meant Titan because there's like methane lakes.
Yeah, methane lakes.
That's
on
cool.
Titan. Yeah, that's on Titan.
So
okay,
that'd be kind of nice to go to.
Yeah, that would be dope. That'd be crazy.
Plus, you got Saturn as an orbiting planet around in the sky, so that's kind of cool.
Okay, so the next question is kind of a combination between two questions because it's very similar. Is it possible to sustain human life elsewhere? And one person asked, especially like the Martian, like, is that possible? Would that be possible?
So yes,
I think,
this is, I mean, it's kind of demonstrated. Musk is trying to do. Yeah, but it's demonstrated by the ISS that you can live in space, I guess.
I mean, when they say
that doesn't really count, though.
No, I think when he means sustain human life, I think they mean like without all that shenanigans. Because, bro, like, I don't think anyone wants to live, in a spacesuit. Or technically, if you're inside the place, like, that's still a weird environment to live in. I mean, I don't know. I think what he means by this is human life, able to exist in other places. And
the key word here is exoplanet.
Oh.
And there are tons and tons of exoplanets, which are planets not in our solar system that have similar qualities to Earth, that are at the right distance away from their star, and they
Star's
could
good.
potentially
Yeah.
be a host
Yeah.
to life forms.
It's just so far that we can't really tell.
Yeah, that's right.
Yeah,
So the only way that we could answer that question for sure would be if we were to visit an exoplanet, see trees, for example,
Or see something.
Yeah,
see something
Yeah.
Yeah.
Right. Next
Okay, next question.
Favorite mathematical equation or theory?
Oh, wow.
Favorite theory, probably quantum theory.
Wow, you really pulled out the quantum theory, eh?
Yeah. I don't know what my favorite equation, probably the classic e to the I phi.
Oh my, Euler.
E to the
bro.
I pi minus 1 is equal
classic.
to 0.
You're a
Or no,
classic
plus 1.
physicist, bro. You're a basic
Plus 1
physicist.
is equal to 0.
Gee.
But yeah, favorite theory, quantum theory. I just think, learning quantum mechanics is hard, but it's doable. You got to really get your brain into a probabilistic way of thinking. So
For sure.
Yeah.
So my favorite equation. Okay, I'm gonna do theory first. My favorite theory is the general theory of relativity. I think that is insane. Also because Einstein just broke everybody's minds with that theory. Because he basically said, yo, gravity does not exist. And he said that in the most elegant way possible in the paper of general theory of relativity. Like, beautiful theory. Einstein's field equations, awesomely written. It's just super cool to think about. Also,
right.
a good recommendation on gravity is the new Veritasium video. I have to share this because it is just so good. It visualizes gravity so well. The new Veritasium video is why gravity is not a force or something like that, and it is a must watch. So yeah, so that's my favorite theory. Favorite equation, I don't really know. Like, I
just pick one. E equals mc squared.
I was gonna say that, but that's not even the actual special relativity equation. It's E squared. That's that one. It's the whole thing.
E equals gamma mc squared.
Oh yeah, that's the one. Okay.
Right.
No, my favorite. Okay, sure. Favorite equation is the time dilation equation. I'm gonna say that because I think time dilation is really cool. The fact that
awesome.
how time depends on velocity and everything. Yeah. So that's my favorite equation. Yep.
Yeah.
Okay.
Next question. What has been your most difficult subject to learn? Probably quantum mechanics.
Yep.
Yeah.
I second that.
Last year when we were learning it, it was kind of just thrown in our face. They're like, this is the Schrodinger equation. And then I was like, how? How does this happen?
For sure.
A lot of questions I had to ask, and how I really got to understanding it was just like, I just stopped asking questions and I just let the math kind of unfold, and then I kind of got like an understanding. I was like, okay, well, if I just accept these rules, everything kind of falls into place.
Also, our second year quantum mechanics course has also been a very big help in this regard.
Yeah, very, very big
help. Very big help in this regard.
I think starting with states and polarization and interference is a lot better than just saying this is the Schrodinger equation.
Yeah, for sure. Okay,
yeah,
so
awesome.
For me, well, it wasn't really difficult. It was just different. Mat 137, or my first year calculus course, because it involved a lot of proofs. It was just difficult is kind of the wrong word. Maybe that's not the right course to describe for this question, but it was a very different course that I wasn't really used to. So it was difficult, I guess, in the beginning for sure. And then how I got it, well, I still haven't. I don't think anyone has just got it just yet. We're still getting it. We're still in the process of getting it. But I think just practice, more and more practice of proofs, and just finishing the first year, just finishing 137, I think was a really good way to get proofs, because I think like they summed it up and all pretty well. So yeah, that's my answer. Okay, next question. After a really long time, like unimaginably long, will the universe slowly become one big galaxy? As far as we know right now, what could happen?
I have an answer to this.
Go for it.
There's actually a YouTube video that you can watch, which is kind of like a logarithmic time lapse of the universe and theoretically what will happen. And actually, because of the nature of stars, they release energy every single second of the day and night, including black holes through Hawking radiation. And so that energy goes into space. But because of the, I think, first law of thermodynamics, something like that.
I always get it mixed up.
Heat only transfers from hot to cold. You can't have a cold object transfer heat to another object, right? Like for example, if you have an ice cube and your hand, the heat from your hand goes to the ice cube. It's not the other way around, right? The ice cube doesn't get colder and your hand gets that energy from the ice cube. It always goes one way. And so because of that, stars eventually, in a very, very long time, will all just die out, and black holes also. When the universe is going to be just a dark place with just black holes roaming around, and then eventually the black holes will just faint into nothing, then everything is just going to be one soup of matter just floating around.
Well, technically also, as we call it, the universe is quote unquote expanding, right? Because these galaxies that we can see are moving farther away from each other. So if in an unimaginably long time, if this just forever continues, because remember the reason we say that this is occurring is because of, dark energy and stuff like that. And dark energy is what's propelling the universe's expansion and causing all these galaxies to, being ripped apart from each other. So in unimaginably long time, we could say, if this just keeps on continuing, that the universe would just be frozen, because there would be so much dark matter, or so much just space, empty space in the universe, that, basically all the galaxies, all the stars are also so far away from each other that they just can't heat up. So the theory is actually called the Big Freeze. That's actually a pretty famous theory that people might have heard of before, where the universe just expands and then it has nothing to do, so it just cools down.
Yeah, and the density of the universe would just be very close to zero.
Yeah.
There'd just be so few particles everywhere you go that there's basically just nothing.
Yeah, exactly. So
we have come to our last question now.
But okay.
Yeah. We have now arrived to our last question, which is on nanotechnology.
Okay, so this is another question where we don't really know what we're talking about, but we shall give our best idea.
But you know what I know for sure?
What?
There will be nanobots in the coronavirus vaccines.
Oh, yes. Of sorts.
So be careful. That was a joke if you took that seriously.
I was fully taking it. Wait, I was thinking of. Oh, that's what you mean.
Like nano robots, Ray, that take over your brain.
I fully just got it. I thought you meant antibodies in the coronavirus. So I'm like, yes, of course, there will be antibodies in the vaccine.
No.
That's what I thought you said. Sorry, nanobots. Yes, no, there will not be nanobots in your vaccine.
Nanotechnology is just small technology. Usually used, well, not usually, because it's not really hasn't been mastered to a degree of fine perfection yet. But it's in the future. There will be mini robots that will be able to go into your body and destroy a tumor or fix some genes or whatever. People are scared of it because it could take over your brain and
and all that kind of stuff. But
you'd become a zombie.
I think
with nanobots.
I think nanotech was like the idea was posed by Richard Feynman when he was just thinking about, just small things, just quantum mechanics in general. Because nanotech basically just stems from making really tiny things do very complicated tasks, hopefully, right? I mean, and then if a collection of them can do these complicated tasks, just like Parker said, send like these nanobots in your brain and it can remove a tumor or something like that. Mm-hmm. So I think nanotech is coming in the future for sure. I think it's a really cool technology. But I don't think it's something to be afraid of, unless, obviously, I mean, in like 3,000 years, who knows? Maybe they'll be selling like nanobots on eBay. Like, remove brain tumor yourself, buy nanobot.
My personal opinion
or something
is
like
that people should be scared of technology.
Yeah, for sure.
They should be protecting their data. No, we are not sponsored by
No, we are not.
But
I swear I just thought we were going to go into a segue. I'm like, wait, we're not sponsored.
But yeah, protect your data. Stay away from Facebook and things like that. They are just trying to steal your information. All right, that is a good place to end the podcast.
We actually answered all the questions. We didn't do it in 30 minutes, but I think we're okay with 40-minute podcasts from now on.
It's fine.
So
let's make this outro short and sweet.
Yep.
Make sure to follow on Instagram at math.physics.podcast, email uft.math.physics@gmail.com. Make sure to follow on Spotify, Podbean, Apple, anywhere you're listening to this podcast right now. Leave a comment on YouTube, anywhere you find a comment section. Leave a comment, ask a question. We will address your questions. This has been
also quick reminder, 900 followers.
Ooh.
Smash that follow button. Try to get us to 1K.
1K.
It's going to be insane.
We like those numbers, all right? This has been episode number 31 of the Math and Physics podcast. I am your host, Parker.
And I am Ray. And we will see you soon.
See ya.